So I lecture on material that I'm lecturing on right now. I've already lectured on it twice, but one of the times that I lectured yesterday, I was having huge internet problems, constant internet problems. And those constant internet problems were just causing all kinds of issues with the class. And so I didn't get anywhere near as far as I got today. And then I'll do a very similar lecture this afternoon. And then I will post one of those lectures, whichever one I think is the best, probably today's, the one we're doing right now. I'll post whatever one I think is the best because they're very, very similar. And so it's worth just, right, it's worth, wow, what did I do? I didn't want to do that. I pushed the wrong thing somewhere. But anyway, I didn't really want to do, I want to do the best lecture and post it once and then make it available to people as best I can. I'm looking down the list to see who's recently joined us, and I don't see who it is. Let me look at my attendance list here. 3, 6, 9, 12, 15. Then there's me, that's 16. And then there's somebody else that I haven't listed yet. I know who it is. Okay. All right. Sorry, I appreciate your patience with me. But I am actually presenting now, so I hope you can see me. And I am recording now, so that there's a possibility, certainly, that I will post this exact lecture. So let me first start by telling you this. I have had some internet problems just since yesterday. And I'm not really sure why. And I spent time trying to deal with the IT people and all that to try and get those problems solved, because they were big problems. Yesterday in both of my classes, the morning class, the afternoon class, and the night class, I had problems with connectivity, and that connectivity problem was such that I ended up, the class basically just crashed, and we lost the class, and I had to start again, really, and go back to square one and start a brand new meeting and send out a brand new link and all that kind of stuff. So I'm kind of hoping that that is not going to happen today. It did not happen in my 11:15 class, and so I'm kind of confident that it's probably not going to happen in this class either. But I do want to set up some ground rules, which is that if we should somehow crash in the first 90% of the class, however that lasts, however long that lasts, if we should crash in the first 90% of the class, then I'm going to immediately send you a new link, and that new link, I will immediately send you a new link, and then you would please come back to class, okay? Yesterday, the internet connectivity ended. I had significant amount of class left, so I didn't know what else to do except to start a brand new meeting, send out new information. And then by the time, it probably took me, I don't know, I want to say that it took me 10 minutes to get everything all set up again. I never was able to reclaim about half the class. And I'm sure it's just because I never said anything about it, because I didn't expect it to happen. I mean, I've so far, since we started virtual classes, I've taught 2, 4, 6, 8, 16. I had taught 16 classes before that, and didn't have a single connectivity problem at all. Something right on my screen that's bugging me. I didn't have any connectivity problems at all. Then yesterday, bang, it hit, and it was multiple connectivity problems in the afternoon and in the nighttime too. So the bottom line is if we could disconnect third of the way through the class, half the way through the class, 3/4 of the way through the class, then I am going to immediately re-engage and send out a new link. So please rejoin me, okay? If it happens to crash in the last 10 minutes of class or something, when we're thinking about the clock and all that, 4:55, if it happens to crash in the last 10 minutes of class, then forget it. I'm not going to try and reclaim the class at that particular point in time. But I just want you to be aware of it. What else do I want to say? Of course, there's plenty of things to say, but let me talk about the normal quizzy type stuff and all that. I'm assuming everybody can see everything and you can hear me well. Again, if you have a question, please immediately open your microphone and ask the question. So just don't hesitate. Can't raise your hands in here. You just have to open your microphone and ask the question. Okay, so just don't worry about interrupting me. Go ahead and ask the question. All right. So we've got plenty of people here now. I want to get started. We've got 17 students here, and I'm sure there's going to be more coming in. I just have no doubt about that. But for now, I think it'd be a good thing to just get started. So what I was saying initially about the internet, if we should crash, I mean, if suddenly I disappear and it's uncorrectable, then I'm going to send you a new link and we will restart again. Okay, and we'll start from where we left off again. If anybody again has any questions, just activate your mic and go ahead and ask, or you could ask a question on the chat line because I'm pretty aware of the chat line going on. It makes me aware of it. I did in fact post the last lecture that I did on YouTube. And I'm going to show you the link on the PowerPoint that's next to me. And that link is good, meaning if you go to this link right here, it is a good link. It will take you right to the very beginning of the last lecture on YouTube. I am working on getting things posted on YouTube, but it's not as easy as it sounds. I mean, when I do the lecture like this and I ask it to be recorded, and probably about a half hour after the class is over, they send me a copy of that recording. Then I need to download it, and that can take a while. It doesn't, it's a big file, and so it probably takes 20 minutes to download it. Then I have to upload it onto YouTube. And that's not complicated. I mean, it was very easy to figure out how to do it. That's not complicated. But the bottom line is it takes like 3.5 hours to upload to YouTube. I mean, it takes a long time. These are big files. They're 2.5 hours long-ish, and they are big files, and they take over 3 hours to upload to YouTube. Once I know those links, I will let you know about them. The links themselves don't include any information about the class. They're just a weird link that's probably computer generated. And so anyway, I'll let you know about them. So over on my PowerPoint here, it does say lecture 4 and the YouTube link. And the YouTube link that's there is good because I copied it straight off of YouTube. When I had to retype it earlier today, I screwed it up. And the students were saying to me, it doesn't work, the link doesn't work. And I went back and go, oh yeah, I forgot this, I forgot that. Copying those links over is a huge pain. But, all right, so I mentioned that. I just want to make sure everybody's doing okay. I still personally don't know anybody who has the virus. I mean, I may know people who have the virus, but they don't know they have the virus. Right? I just don't know anybody yet who has the virus, and I think that's a good thing. I've asked the same question to other classes, and almost nobody can really tell me somebody who they are 100% sure has the virus. I mean, it's always sort of my cousin's ex-wife's daughter, we think she has the virus, but mean, as far as people actually going, yeah, my brother has it or something like that. I have not heard that yet. And honestly, I think that's a good sign. I mean, so Grace, you specifically know somebody who does? Is it a member of your family or a relative or? Grace just told me that she knows somebody who does have the virus. And I was trying to be optimistic and think, well, I don't know anybody who has the virus, so many people must not have the virus or whatever. I do think that we are, so she answered that it was a family member out of state. But still, I mean, I think we're lucky, and I'm sorry to hear about that, Grace, that any member of your family has the virus. I'm sad to say I think we're all going to have members of our family that have the virus sooner or later, I think. I think one good thing that happened is when these eastern cities like New York City, which is, a petri plate at best, when these eastern cities started to have big outbreaks, the western cities like Seattle and San Francisco and Phoenix and Tucson and Salt Lake City and these western cities, they didn't wait. They jumped right on the bandwagon and said, "Forget it. We're having social distancing. We're having social distancing. We are going to encourage people to wear gloves, to wear masks, etc." And so I'm kind of hoping that out here, I'm not naive. We certainly will have people who have the virus, but I think that the social distancing and the other things that we're doing, or that we're being forced to do, are helping. So anyway, the bottom line is that that I think that when it comes to flattening the curve and not overwhelming the healthcare system, that we're doing pretty good out here. I mean, I have no choice but to go out and about. I need to bring food and medicine to my elderly mother who's in isolation. And so I noticed the things they're doing out there, like you go to the Circle K and they've got, tape on the floor that's 6 feet apart, and they want you to be 6 feet apart. You go to Trader Joe's and you stand in a line 6 feet from somebody else, and they only let a few people in at once. And so there's not ever a big crowd in there. It's easy to maintain your social distancing when you're in a grocery store like that. I mean, I've seen so many grocery stores that now have like a plexiglass shield between you and the cashier. So these are all good things that will, as they say, flatten the curve out here and make it less devastating for us. So I'm just taking a look. Sarah was saying there's South Tucson is Tucson's hotspot. I guess I haven't been following the news. Following the news as closely as I could in terms of what's happening here in Tucson. But I just think we need to continue doing what we're doing, which is social distance. And, when I'm out and I'm doing work for my mother, I wear a mask and I wear gloves and I cover myself with Purell and do all that kind of stuff. And I feel like I'm running out of Purell, but then I guess I have to make my own out of tequila. But anyway, the bottom line is that I'm hoping everybody's doing okay. Right, still logging people in, and that's just plain fine. I feel like there's somebody on the list that I'm missing. So, but that's okay. We've got 18 people accounted for. Well, actually, no. 3, 6, 9, 12, 15, 18, and me. That's 19. So I guess I've accounted for everybody. All right, so look, let's go over to this PowerPoint that's here, and I'm going to go back to the first page. This is the first slide in the PowerPoint that says Coronavirus Lecture 5, cell organelle structure and function plus cell membrane transport. And you know what? Really, I should have renamed this because it's not cell organelle structure and function anymore. We're done with that. We finished Goldenrod Packet page 21. And all the sort of anatomy of cell organelles and the function of cell organelles. We finished that last week. This is really cell membrane transport. And I'm actually going to probably continue using this same PowerPoint next time because we won't finish it today. It's a pretty long PowerPoint. And we'll finish it up next time. But I'll name it as Coronavirus Lecture 6, Cell Membrane Transport.2, change the dates, put some other things in. But let's go to class business, because here's class business for yesterday and today. Remember, my Monday and Tuesday classes are usually pretty much in sync. Even though we started a week, the Tuesday, Thursday classes started and had almost a full week of classes before the Monday, Wednesday class met. That's the reason why we've got quiz, 6, 7, 7, 8, 8, 9, etc. because of that. They're the same quiz, but they just are different numbers. In the Tuesday, Thursday class, we took a quiz a full week before the Monday, Wednesday class took a quiz. So just for the record, thought questions A14 through A21 are ones that we're going to cover today, and I think we will, we'll make pretty good progress on those, if not completely finish them. Then down here where it says quiz for, darn it, blow this up a little bit, okay? So it says quiz for Tuesday, Thursday class, Tuesday, April 14th, due back by Thursday, April 16th. Okay, and I haven't posted that yet, but believe me, as soon as we are done with class, or maybe even during our break, I will get that posted. Okay, so quiz number 9, because that's where we are, quiz number 9 is going to be posted very, very soon, meaning today, right? And it's due back in a little less than 48 hours, really. It's due back before the next class by email. Now, just so you're aware, the way I'm going to make this quiz available is by posting it on my PIMA. And it will be in the exam 2 handouts. And make a note, it's going to be document number 008. So I'm loading this stuff up front, so you don't have to dig through a long list of things to find it. So, 006 is this PowerPoint. 007 is the quiz 7-8 key. 008 is quiz 8 and 9. Quiz 009 is going to be the quiz 8 and 9 key. So, I'm just stacking things up that way at the top of the list, so you don't have to go digging down through all those other documents. All right. So, anyway, as soon as the class is over, I will post that quiz right here. Okay. Then we are going to be looking in some detail today at Goldenrod Packet page 23 and 24. So I'm hoping you have your Goldenrod Packet ready to go. I will also be showing you some documents from my PIMA Exam 2 posts. And every time I show you one of those documents, I will tell you what document number it is. Okay, so that you can get access to it pretty easily. And again, I mean, I was kind of blown away in the last class I met, because there was a student who didn't seem to understand the whole my PIMA thing and said, I've been looking all over D2L for your stuff, Steve. And I said, sorry, the only thing you're going to find in D2L from me is grades. Everything else is posted on my PIMA. So we walked through how to get back there. And the thing that made me sort of maybe incredulous was that, we're 3/4 of the way through the class. And this person, it sounded to me as if maybe they'd never even looked at one of those beautiful quiz keys that I posted that has bonus answers for the next quiz and all that. And that's too bad, because I know many people who have told me, look, Steve, I use those bonus answers, and that helped me do better on the upcoming quiz. And then here it is, lecture 4, like I said, right down here at the bottom is lecture 4 posted on YouTube. And despite the fact that it took hours to get it posted and everything, it is up there now. And I'm pretty sure this link that's right here is a perfectly good link. And I can't jump right off this PowerPoint to it, I don't think. I could copy it and paste it into the search line and go to it that way. But I'll tell you, if you make the tiniest little mistake here, like if you put a G here instead of the Q, believe me, you won't get the video. So you got to make sure everything is exactly like this. Best to just copy it and paste it. And once you've done that, you'll be able to access it. So this was lecture 4. And I am going to work backwards and get lecture 3, lecture 2, lecture 1 up and all that, but it's not difficult to do it. It's just time consuming. And when you're doing it, it's like you can't use a computer for anything else practically. Behind me, I've got a computer that's running, and it's supposedly uploading another lecture from a different class, and it told me immediately it was going to be 3.5 hours to upload it. So I'm just letting it do its thing, and I was worried it might interfere with my internet connectivity, but it didn't. Okay. Anyway, any questions about the class business that's posted right here? Lots of things that you're looking at. So thought questions, goldenrod packet.
So you had said that quiz key for quiz 8 would be posted today?
No. Oh, wait a minute. The quiz 7-8 key is already posted. It's document 007. So quiz 8 key, it's actually called the quiz 7/8 key, is posted as document number 007. Were you unable to find it?
No, I just found it right now. I was just logging in.
Okay, good. It's there. And then I'm obviously not going to post the key to the next quiz until Thursday. I'm going to send you the brand new quiz as soon as I'm done here today. But thanks for asking. Okay, so I'm happy to answer any questions about the class business for sure. Anything that's unclear. And then when I show you documents that come straight off my PIMA, I will make a point of showing you what the numbers are on those documents, okay? Okay, so here we go. Now we can leave this class business and go into the actual content for the class. I want to make sure I've covered any kind of the logistical stuff that needs to be covered. But today we're going to be talking about transport across membranes, the movement of things across membranes. Last week, we spent the entire week thinking about last week thinking about cell organelle stuff and anatomy and physiology. And so, I guess I'll just use this document here as a document to post, okay, or a document to pull up. I'm pretty sure everybody can see it at some level, or I hope everybody can see it. Tiny bit smaller. There we go. All right, so let's find me again. I want to make sure I'm back there, hiding in the background. So I just pulled this up because it reminds me of last week. Here is a really nice cell drawing done by a member of the adjunct faculty years ago. I used to work with. She and I worked on several books about cells and anatomy and physiology, et cetera. And the company that we worked for at that time let us use this picture of the cell. She did a great job of drawing this picture. She was a great scientific illustrator. Well, she's still alive. I don't want to pretend that she's dead. But anyway, you can kind of look into this cell and see things like the nucleus with nuclear pores, and you can see chromatin and the nucleolus. You can see a centriole and a Golgi complex with Golgi vesicles, rough endoplasmic reticulum, smooth endoplasmic reticulum, mitochondria, peroxisomes, lysosomes, the whole story. Oh, and these things over here, which I think probably represent microvilli. Now, this is a document that you have. This is document number 11 in the on the MyPIMA documents in the exam 2 posts. Okay, so this document is, should you want to look at it and study it, it is available for you, and you just need to go to MyPIMA and find it. So just to sort of reconnect, that's what we were working on last week, the anatomy and physiology of cell organelles. Well, now what we're going to do today is we're going to move from all the organelles and we're going to move over to the edge of the cell here. And the edge of the cell here means that we're looking at the cell membrane, okay? put this down here. We're going to be spending a lot of time today talking about cell membrane transport, cell membranes, etc. Now, look, the title here, Transport Across Membranes, I could have called this Cell Membrane Transport. I could have called this Cell Membrane Activities. I could have called these Cell Membrane Transport Activities. Oh my gosh. Bunch of different ways to refer to it, but it all has to do with stuff that's happening around the membrane of the cell. And this has to do basically with the idea that there's different conditions inside and outside the cell that have to be maintained for homeostasis. I'm going to show you a graphic in a few minutes. So different conditions, the concentration of stuff inside a cell is not necessarily exactly equal to the concentration of stuff outside the cell. There's a continuous exchange of ions, salt, sugars, and other molecules between the inside and the outside of the cell. Things are moving across this membrane all the time. These ions, salt, sugars, and other dissolved stuff, which we refer to as solutes. Solutes are the dissolved stuff in the intracellular solution or the extracellular solution. So these different solutes are found all around the cell. So here's a diagram that I pulled out of one of Guyton's medical physiology textbooks that I've always really thought was interesting. And let me just get you oriented to it. And by the way, let me say it right now. You do not need to know any of these numbers. You don't need to know anything from this chart really, except the big take-home message that the extracellular fluid and the intracellular fluid are quite a bit different. So anyway, here is a cell, this grayish thing. This is the nucleus and the nuclear membrane and the cytoplasm. This is what we would refer to as the intracellular fluid, the kind of solution that's inside the cell. And it's the intracellular fluid solution. Now, this line right here is the cell membrane, right? That one line. And then if we are inside the cell, we're in the intracellular environment, in the intracellular fluid. If we go on the other side of this membrane, we're in the extracellular fluid, the extracellular solution, the mixture of stuff that's outside the cell. And as I said, one of the big take-home messages is this one. Look, sodium ion, 142 milliequivalents in the extracellular fluid, 10 milliequivalents in the intracellular fluid. There is 14 times more sodium in the extracellular fluid than in the intracellular fluid. Now, look at potassium, another ion we've talked about. 4 milliequivalents in the extracellular fluid solution and 140 milliequivalents in the intracellular fluid solution. 4 and 140, that's 35 times more potassium inside the cell than outside the cell. Sooner or later, I'm going to tell you that there's a specialized pump, and you're not going to be surprised. It's called the sodium-potassium pump. And you know what it does all the time when it's working? It pumps sodium out of the cell, and it pumps potassium into the cell. Now look at calcium, 2.4 milliequivalents outside and 0.0001 milliequivalents inside. There are thousands of times more calcium outside the cell than inside the cell. Magnesium, not as dramatic, but 1.2 milliequivalents outside, 58 milliequivalents inside. There's about 50 times more inside than outside. Chloride, 103 outside, 4 inside, 25 times more outside than inside. And these same basic patterns persist for all of these. I mean, there's different oxygen concentrations, there's different carbon dioxide concentrations, slightly different pH, things like glucose. Here's the homeostasis value for glucose. I might have referred to it as 100 milligrams per deciliter, but 90 milligrams per deciliter. But inside, 0 milligrams per deciliter, and that's because glucose is a molecule that as soon as it gets in a cell, it gets broken apart. It is no longer glucose. Anyway, like I said, the big take-home message here is there are huge differences between the concentration of things in the extra and intracellular fluids. How does this happen? Well, I'm just so tempted to point to this little line here, this little black line, and go, that's what makes it happen. This line right here, the cell membrane, is what makes this happen. Remember, the cell membrane is a semi-permeable or selectively permeable membrane. It does not let some things through. It lets other things through. It deliberately pushes some things through or pushes them out, and it doesn't do that to other things. A selectively permeable membrane selects what goes in and out of the cell. Okay, so quick review. Types of transport across membranes. I'm actually going to jump down here to a document that I'd like to show you. It's this document. And this document is Goldenrod packet, page 23. Right? Goldenrod packet, page 23. It's called Cell Membrane Transport Processes. So you have this available to you in front of you. Cell membrane transport processes. These processes, like diffusion, osmosis, carrier-facilitated diffusion, active transport, receptor-mediated endocytosis, pinocytosis, phagocytosis, exocytosis, these have generally been grouped into two big groups: the passive cell membrane transport processes and the active cell membrane transport processes. What does passive mean? Passive means that the cell does not need to expend energy to make these things happen. They happen thanks to energy from the universe. There is the molecules of the biosphere are constantly moving in motion, and that energy, which is sometimes called kinetic energy or movement energy, there's lots of kinetic energy and movement energy out there in the biosphere and in the universe. And so that's where the energy comes from. I mean, it sounds kind of new agey or whatever, but if you were to ask, if you were to ask me, look, where does the energy for diffusion, osmosis, or carrier-facilitated diffusion come from? I would say it comes from the universe, right? The universe provideth this energy for diffusion, osmosis, and carrier-facilitated diffusion. And that means the cell doesn't need to expend energy. Now, these other processes are active processes, and active means energy from the cell is required. The cell will have to use ATPs to make these things happen. The cell has it has to put energy to make these, has to use energy, supply energy to make these things happen. You know, a pretty significant part of a cell's energy budget, maybe as much as 50%, can be devoted to cell membrane transport processes like active transport, receptor-mediated endocytosis, pinocytosis, phagocytosis, or exocytosis. Now, we're going to talk about all of these, but let me just show you down here on the bottom of the page and on the next page too, the back page, are definitions of diffusion, the law of diffusion, osmosis, law of osmosis, carrier-facilitated diffusion, active transport, receptor-mediated endocytosis. So some of these things that I'm talking about, I have written a definition right there for you. On the back side of this page is this document, which includes the definitions for pinocytosis, phagocytosis, exocytosis, and it includes this chart, which we may get to talk about today, depending on how efficient I am. And this document, or this chart, is called the 3 osmotic scenarios. And like I said, if we can get to this far and we look at this chart today, that would be wonderful. All right, I'm going to shrink this. So I want you to know that on Goldenrod packet page 23 and 24 is material that I've provided for you, definitions, descriptions that I've provided for you, and other kinds of information too. Okay? All right, so let's just zoom through this. Types of transport across membranes: diffusion, There can be unaided diffusion, meaning that the molecules just diffuse right through the cell membrane, no help. Or it can be what's called carrier-facilitated diffusion. And in carrier-facilitated diffusion, a special protein carrier helps diffusion happen, all right? And of course, remember, diffusion does not require energy, so it will happen without the help of any energy from the universe. There's osmosis, which is the diffusion of water through a cell membrane. We're going to talk about it today. There's active transport through pumps. When we look at things like sodium and potassium, they're odd. Look at sodium and potassium. They're ions. It's hard to get those across membranes. If you want to, you're going to need to use some kind of active transport pump. An active transport, the word active in it says everything. It says that pump runs on cellular energy. Then there's various kinds of endocytosis, the ways cells bring things into the body of the cell, like receptor-mediated endocytosis, phagocytosis, and pinocytosis. And just ignore this, see handout page 8. I left that in by accident. Okay. Remember, if anybody has any questions, I'm hoping you will just activate your mic and jump on in. This is kind of review, jumping from my document to this PowerPoint right here. All right. So, transport across membranes. There's passive transport, which you talked about, doesn't require chemical energy. Diffusion, osmosis, and carrier-facilitated diffusion are all in the passive transport category. Active transport requires cellular energy in the form of ATPs. That requires energy. The energy is provided by ATP. This includes active transport. 3 types of endocytosis, the way we bring special things inside the cell, and then exocytosis, the way we throw stuff out of the cell. But all of these require energy. So what kind of energy? I mentioned this earlier. It's often called kinetic energy, a kind of energy that's responsible for random molecular movement. I mean, here's the thing. You already know this. The universe is in motion. Atoms are in motion. Electrons are orbiting around the atomic nucleus at 2,000 meters per second. Movement and the energy associated with movement is absolutely a common state in the universe, and that means on Earth and in our bodies and all that. When molecules move, they bump into each other. Energy passes from one molecule to another. They fly away. This kind of random molecular movement is called Brownian movement. And Brownian movement is just the name given to a very special, this idea that particles, molecules, atoms are in constant movement because there's kinetic energy. And as I said, it's called Brownian motion or Brownian movement. When we start to think about the actual movement of substances, we need to understand some vocabulary related to what's called the concentration gradient. Concentration gradient is an unequal distribution of certain molecules between 2 areas. So, you know, if you look and see that there's, in one area, there's 100 molecules per milliliter, and in a different area, there's 1,000 molecules per milliliter, then you'll say, okay, there's a higher concentration of atoms in this location compared to this location, and that means there's a concentration gradient. When the concentration of molecules are equally distributed all over, it's said to be in equilibrium. So diffusion. Let's talk a little bit about diffusion. Diffusion is the movement of molecules from an area where they're more concentrated to an area where they are less concentrated. The energy that makes this happen, the movement of molecules like this, is supplied by the random molecular movement of kinetic energy, the idea that the universe itself is in motion at the atomic level. Oh, the law of diffusion. I want to talk about the law of diffusion, which it really should be called Mackey's law of diffusion, since it was me who proposed it, right? But nobody wants to give me any credit for it. The law of diffusion is obviously related to the concept of diffusion. So, diffusion, I'm going to magnify this up a little bit. Diffusion is a physical process in which substances, I mean atoms and molecules, move from where they are more concentrated to where they are less concentrated. I mean, what makes this happen? Well, the universe is in constant motion at the atomic level, and stuff, whatever it is, gets randomly distributed over time. So a silly little drawing here. Here's a bunch of molecules all clustered pretty closely together. Here's what happens if you give them time to do it. They end up, spreading themselves out in a more, in a random way. So, like it says here, the universe is in constant motion at the atomic level, and therefore stuff, whatever that is, molecules and atoms, gets randomly distributed over time. So this is such an important process that it inspired me to create Mackey's law of diffusion, which I sometimes just abbreviated as this, not LOL, but LOD, law of diffusion. And the law of diffusion says this: substances will move from where they are more concentrated to where they are less concentrated if they can. So you can prevent diffusion from happening. You can build a wall that prevents some odor from diffusing from one room to another. When I think about diffusion, I think it's important to point out that this is something that we can observe every day. It's true, we're talking about cells and diffusion around cell membranes, but we don't want to ignore the fact that diffusion happens everywhere. So, for example, when I come home and I open the front door of my house, I can immediately tell if there are litter boxes that are in bad shape and need to be cleaned. Why? Because the molecules associated with urine or feces, they will diffuse into the air and travel throughout your house. If you give them a chance, they will travel throughout your house. So as soon as I open the door, I can immediately smell the smells that I associate very specifically with litter box, that needs to be cleaned. When I was a kid, I felt like I had to get up really early in the morning to go to school. And sometimes it would be, I lived in New England, and so sometimes I'd have to hike through snow or whatever. So we got up at like 5:45, a ridiculous time. But that's the time I had to get up in order to get to school. And every day I hated it. Believe me, I don't like getting up hardly whatever time it is, but I didn't like getting up at 5:45. So I would have the same discussion with myself almost every day. I would say, look, Steve, on the weekend, you're going to sleep as late as you want. You're going to sleep all day on Saturday. You'll sleep until 2 o'clock in the afternoon just to make up for this awful thing of getting up at 5:45 in the morning, Monday, Tuesday, Wednesday, Thursday, Friday. Well, so finally Saturday would come, and I would be thinking, I am going to sleep until noon, but I would be laying in bed early and, at 7 o'clock or 7:30 and thinking, I don't feel like sleeping anymore. But one thing that always got me out of bed on Saturday mornings was the smell of bacon cooking. And that smell got to me in my room under my covers by diffusion. So here's what it looked like. Where my mother was in the kitchen, hovering patiently over a cast iron skillet and cooking bacon for breakfast. Those bacon molecules were very highly concentrated in the kitchen around that cast iron skillet, and very high concentration. But believe it or not, those molecules associated with bacon smell, they would diffuse out of the kitchen, across the living room, up the stairs, down the hall, underneath that little 1 centimeter crack beneath my door. Then they would manage to diffuse across the carpet, and when I inhaled, they went up under the covers and wedged in my nose. And I immediately recognized that smell and said, oh my gosh, it's bacon. I better get up now, or I'm not going to get any bacon. My brothers are going to eat it all. The bottom line is that the way those molecules got to me a long distance away from where they were being cooked was by the process of diffusion. They diffused from the kitchen where they were highly concentrated to the dining room, the living room, up the stairs, et cetera, et cetera. They were moving by diffusion. Okay, so when we're talking about diffusion and the law of diffusion, let's talk about some observable patterns in diffusion behavior. So, for example, big molecules diffuse slower than small molecules. Now, you know what? Let me just be careful to phrase something specific, okay? When molecules move from high concentration to low concentration, it does require energy to make that happen. But the energy for this kind of diffusion, like bacon diffusion or litter box stink diffusion, that energy is coming straight from the universe. It is kinetic energy provided by the universe, not for the purpose of diffusion necessarily, but the result is diffusion. So you won't be surprised when you hear that big molecules diffuse slower than small molecules, because it takes more energy to move a couch than it does to move a chair, right? The bigger something is, the more energy it's going to take to move it. And so big molecules diffuse slower than small molecules. Second statement, it says, as temperature increases, diffusion rate increases. What? As the temperature goes up, the diffusion rate goes up. And honestly, it's back to energy. When you say the temperature is going up, what you're really saying is that the amount of energy in the air is going up. And if there's more energy in the air, then it will encourage diffusion rate to increase. So increased temperature means increased diffusion rate. Now, in cell membranes around cells, here are some basic principles. One, gases like oxygen or carbon dioxide diffuse easily and fast. These are molecules that are not polar. They're able to move through cell membranes pretty easily. These specific respiratory gases, which are so important. We're going to talk about those today too. Now, one thing that diffuses really fast and easily is water. And water, that's sort of a surprise to me. Because if you remember, the central core of the fluid mosaic model of the cell membrane is a layer of fatty acids, lipid tails. And those, if anything, should repel water. But nevertheless, when we study the movement of water through membranes, we see a lot of water moving through membranes. That doesn't kind of fit the general model. But here's the thing. It turns out that allowing water to move back and forth across cell membranes, good, is super important to cells. So they've actually built a protein called an aquaporin. The IN says protein, the por says channel or gate, and the aqua, of course, means Aquaman. Well, no, water. Aqua means water. And so water can move fast and easily through cell membranes. And the only way that's possible is if cell membranes install a bunch of these things called aquaporins, proteins that are specialized for water movement. So water, gases like oxygen and carbon dioxide diffuse easily and fast. Ions like sodium, potassium, or chloride. These diffuse much less easily. I mean, they're charged and kind of hydrophilic, and the inner core of a membrane is hydrophobic, and so it kind of repels those charges. If you want to move ions around a cell membrane, you are going to need to build a special channel, or more likely a pump of some kind. Like one of the most famous cell membrane pumps is called the active transport pump, but the most famous one is called the sodium potassium pump. And as you might guess from the data I showed you earlier, what it does is it throws sodium ions out of the cell in a very selective way. It throws potassium ions into the cell in a very selective way. And it allows chloride ions to move in parallel with sodium ions, right? So ions diffuse less easily. Next, larger molecules, well, glucose isn't a huge molecule, neither is amino acids. Proteins can be huge. They diffuse slowly, if at all. I mean, these are molecules that are way too big to wiggle their way through a cell membrane. If you want to get these large molecules, you're going to need to build a special protein carrier. Okay? So this, again, is document number 23 in the Goldenrod packet. The other side, 24, is a page that we'll look at. Sorry, I got that wrong. We'll look at some other documents from MyPima. I was thinking of Goldenrod packet page 23 and 24. This isn't Goldenrod packet page 23. This is MyPima exam 2 post document 23, sorry. I often feel like I'm losing my mind these days, but trying to keep it in touch, trying to stay sane. All right, diffusion. So just as a graphic, take a look. Here's a solution. That means it's got a solute and it has a solvent. Over here, the green round spheres are the solute, the dissolved stuff. And notice that if you give them time, they will move out through the cell, and they will then be in lower concentration, but they'll be everywhere. Over here, they're kind of tightly packed together. And over here, they start to get spread apart, and over here, they are really spread apart. Here we'd say they were high concentration, medium concentration, and lowest concentration. So in this case, like it says, the solute, which is the dissolved stuff, the green circles, is from the left to the right. Right, the movement of the solutes is due to the concentration gradient and the law of diffusion. I mean, imagine you took a sugar cube and you just dropped it into a glass of water and you didn't do anything. You just sat there and watched it. Well, really, two things would be happening. One would be that the sugar cube would be slowly breaking apart and distributing sugar molecules all throughout that glass of water. At the same time, the water outside that sugar cube, which is highly concentrated, it will be slowly working its way into the sugar cube from where it's more concentrated to where it's less concentrated. So you don't need a membrane for diffusion, like I said. It can involve, litter boxes and stuff. But most diffusion processes that we're interested in living organisms take place in water across membranes. So cell membranes are selectively permeable. Remember that? They don't allow everything to move back and forth equally. They select what goes back and forth. The cell membranes allow certain things to cross and they restrict other things. I mean, in a certain sense, the smaller you are, the more likely you are to be able to go across. The more hydrophobic you are, the more likely you'll be able to go across. The more hydrophilic you are, the less likely, and the bigger you are, etc. too. So any kind of passive transport, osmosis, diffusion, carrier-facilitated diffusion, these are all things we're talking about that go across a membrane. So diffusion is the tendency for particles to spread out evenly in an available space from an area of high concentration to an area of low concentration, but from, again, where they are in high concentration to where they are in low concentration. Some of the stuff is stuff that I've already mentioned to you. In this case, this is just a graphic that when you look at it, take a look at what's happening here. Here's a membrane with some membrane openings, no doubt about it. And so if you set this situation up, so you have on the left a high concentration of solutes, that's the dissolved stuff, and a low concentration of water. On this side, on the right, they have a higher concentration of water and a lower concentration of solute. Well, since we're sort of just figuring out solute today, which can be challenging, the solute will be able to move through these openings, respond to the concentration gradient, and move from where they're more concentrated to where they're less concentrated until what? Well, most of the time until they are, until they reach equilibrium. Remember, equilibrium would be where the number of molecules on the left side are the same as the right. I mean, under those conditions, molecules are still going to move back and forth, but you're not going to see a pattern like this where there's lots here and none here, then less here and some here, and now equal numbers here and here. Now, for what it's worth, we're just thinking about the dissolved stuff here, but something else is happening here, and that is that this stuff outside, this stuff right here, this is, this, sorry, I don't know where I'm going with this. I thought I had this profound thought, and then I realized, no, I don't. So molecules will move from higher concentration to lower concentration. That equals the law of diffusion. Remember how we use these brackets here to represent concentration? Higher concentration to lower concentration. That is the essence of the law of diffusion. Okay. Now, another thing that's important to think about is whether membranes are permeable to things. Remember, permeability means, can things move across it? How permeable is it? Are things able to move through the membrane? And there are patterns. Whether or not a substance can cross the membrane depends on several things. One, its size. If it's too big, it just won't fit through. You know, one day I was out in the park, true story, and I just happened to be watching this dog, and the dog was acting kind of, I don't know, odd. It was running and stopping and jumping and this kind of stuff, and I realized why. The dog was chasing a butterfly, and the butterfly was just sort of, you know, it was flying around in kind of a random way. I don't know if the butterfly even was aware this dog was chasing it. It was a big dog. And both of them moved over to the edge of the park. And what amazed me was the butterfly flew right through a chain link fence, but the dog didn't. The dog basically wasn't paying attention. It was chasing that butterfly. The butterfly was little. It went right through the hole in the chain link fence. And then the dog right behind it bashed into that chain link fence. Why? Because it was too big to go through that little hole in the chain link fence that's this big. But the butterfly probably didn't even notice it. It went right on through. If you're too big, you just won't fit through. Another thing is if it's hydrophilic or hydrophobic. Remember, the membrane is hydrophobic inside, and it's a pretty thick layer of fatty acid membrane structure. And so if you are hydrophobic, you can probably go through more easily than if you were hydrophilic. Another thing that determines the permeability, whether things move back and forth across the membrane, is whether there's a concentration gradient. Is there equal amounts of things on both sides of the membrane? If there are, you're not going to really be able to measure much movement. But if there's a higher concentration on one side of the membrane and lower concentration on the other, then that concentration gradient will kind of drive an urge to do diffusion or osmosis. So again, here's a nice phospholipid bilayer. You see it. Here's the hydrophilic head. Here's the extracellular water. Here's the intracellular water. Here's a nice, a really nice round phospholipid head. Here's tails. Here's the tails. These tails overlap mostly with the other tails. So this is that lipid layer. And if you're nonpolar, hydrophobic, then you might just be able to wiggle right through that lipid layer, no problem. You go from outside the cell to inside the cell. But if you're polar, ionized, hydrophilic, forget it. You're not going to be able to just wiggle through the membrane like that. No, the cell is going to have to build a beautiful blue transport protein for you to move through. So these polar ionized hydrophilic stuff, they are going to be transported through the cell membrane, through the cell membrane by this transport protein. So remember, there were two types of passive transport: simple diffusion, where a molecule simply goes right through the membrane; error-facilitated diffusion, where the molecule has to go through a protein channel or pore. There's a carrier that is a protein embedded in the membrane. It goes all the way through. It has a pore for the passage of molecules. The pore can be general, meaning it could accept a lot of molecules of similar size, or it can be really selective and only allow one thing to move through, like the protein that allows glucose to move through. Does somebody have a question?
Yeah, Steve, could you go back to that last slide for a minute?
Of course, I'm happy to. This one.
Yes. I'm trying to understand. Hold on a second.
Okay.
So the phosphate heads are hydrophilic.
So this is hydrophilic right here, you bet.
So how does it get through in the first place?
Well, these, you know what, the thing is that these hydrophilic heads, they are a lot smaller relative to this inner layer of fatty acids. So if you're a molecule that cannot interact in any way with these fatty acids because you're polar, ionized, hydrophilic, then you're never going to go through unless the cell builds a channel for you, which is what this is, a protein channel. Mm-hmm. Now over here, if you're nonpolar, hydrophobic, okay, then you have a very strong urge to move from this area here through and just kind of wiggle past this head and get into the hydrophobic portion of the membrane. Okay, this is a really pretty generalized picture. And it's useful, but it's a pretty generalized picture. So this layer here is much thinner than this layer. So these nonpolar things, they manage to just kind of wiggle through this outermost layer. They're happy to be in here, and then they wiggle through here. Now, why? What is their motivation to go from here to here? I mean, if you want to know that, why is their motivation to go from here to here? And their motivation would be that there's a higher concentration of them here outside the cell than inside the cell. So the energy, the universal energy that powers this is going to power the movement of certain molecules through the membrane in a really straightforward way, and other molecules will try to go through the membrane, but they won't be able to. They try to go through, but they can't. Oh, now we can. Okay. So what I'm pointing to right here, this is the extracellular fluid. This is the intracellular fluid. And then this is the fluid mosaic model of the cell membrane, but it doesn't show cholesterol. But it does show one big protein here and the phospholipid bilayer below it. So these things are motivated to go through because there's more out here than there is in here. Now, if they equal out here and here, then they're going to stop moving. You really won't be able to notice much change at all if they reach equilibrium.
Okay, thank you.
Yeah, I can tell that okay didn't sound like you were totally convinced.
Okay, I have one more question in that, I guess. So just to clarify, so I know that nonpolar molecules like to hang out with other nonpolar molecules, but they don't get stuck in the middle there with all those tails because the force of diffusion or osmosis is stronger than that force of them wanting to stick together.
I would say yes. I think that's good analysis, meaning that they are motivated to get in here, but there is this law of diffusion that says that as they, let's just put it this way, let's say they all move across and they're all in here now, and they're pretty highly concentrated in here compared to here. That's what's going to be that's what's going to motivate them to move out of that and into the cell.
Okay, and that's helpful.
It's as a general principle, I think that's what we how we want to view that. I think your analysis is accurate. All right, so look, here's where we were a minute ago. Okay, I'm going to go back here. And I want you to look at this question down at the bottom. In passive transport, which way would molecules always move relative to their concentration gradient? And we're going to think about that for a few minutes because it's 3:33, and I think that I need to take a break. I don't know about you, but I do. I mean, I have to tell you, I mean, you've known me a while. I move around when I am lecturing. When I'm sitting stuck in a chair, I just can only take it for so long. I got to get up, I got to stretch a little, and I got to move around. So I'm going to encourage you to do the same thing. Get some caffeine, run to the restroom, get up, stretch, whatever, and we'll be back in 10 minutes, okay? All right, that's the plan. I'm back if anybody has any questions. I might be the only one who's back, I suppose. Just took enough time to stretch out my back and legs. Sitting in kind of a cramped little area here. And uh-oh, I see a question. Nice. Well, Sarah, that was very interesting. And you know what? It absolutely is related to what we're talking about. But I'll tell you what actually was going on there with those ciliates is somebody was directing distilled water into their area. And that distilled water, of course, is 100% water. The water inside the ciliate is less than 100%. I mean, it might be 98%, but it's less than 100%. So water starts to flow into the ciliate, and it simply can't remove it fast enough. And that's what causes the cell to swell up and burst like that. In Paramecium, one protist that we've spent a little time talking about, they actually have pumps inside that gather water and expel it as fast as they can. And so, but if you take a ciliate like a protist and it's used to living in pond water, and that pond water might be, let's just say it's 95% water, and you put it in 100% water, then that highly concentrated water is going to flow into that cell. It's going to cause that cell to swell up and explode and kill the cell. Well, that's what's actually going on there. So that was an interesting video and directly related to what we're talking about here, though really it's a special kind of diffusion. It's the kind of diffusion that involves water and cell membranes. We're going to talk about that today, and it's called osmosis. All right. So here's where we were a minute ago, and we talked, and it mentioned simple diffusion, carrier facilitated diffusion. It uses no energy because it's powered by the kinetic energy supplied by the universe through a concentration gradient. And then last question was, in passive transport, which way would molecules always move relative to their concentration gradient? Well, if there's a concentration gradient, it means there's more, let's say, on one side of the membrane than there is on the other. And when there is more in one place than there is in another, it's going to obey the law of diffusion. And the law of diffusion says that things always move from where they are more concentrated to where they are less concentrated. Now, in terms of the actual terminology here, they would say that it's moving down its concentration gradient from high concentration to low concentration. Okay, so the answer is would always move down the concentration gradient from high concentration to low concentration. So in this particular case, look out here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 solute molecules, and here I see 2. More concentrated here than here. Assuming that this protein channel will let this molecule move from where it is more concentrated to where it is less concentrated, then that is a kind of diffusion. And in fact, the diffusion that looks like it's happening here is that special kind of diffusion called carrier-facilitated diffusion. And carrier-facilitated diffusion, well, diffusion means high concentration to low concentration. Carrier means this protein carrier, transporter, channel. And the facilitated means that this blue protein channel helps the diffusion happen, right? Because without this, if this didn't exist, then no diffusion would happen. Too big, it wouldn't go through. But this facilitates the movement. It is carrier-facilitated diffusion. All right, so let's talk about osmosis. And honestly, we were just talking about osmosis. I don't know how many people were back here on time and saw that little video that Sarah had linked us to that showed some ciliated protozoans kind of exploding, and that would certainly kill them. Their death was caused by osmosis, which is the third type of passive transport. So let's talk about osmosis. Remember that most processes in our bodies and in cells take place in water. Most cells, 70 to 85% water, and really depends on exactly how you calculate that out. But beyond a shadow of a doubt, the most common molecule in cells and around the outside of cells is water molecules. Water molecules are pretty small, and they diffuse easily through membranes through small pores. Remember, the name of the pore was an aquaporin. The diffusion of water across a membrane is osmosis. I like the way they phrase this. Osmosis is a kind of diffusion, meaning it obeys the law of diffusion, and things are moving from where they're more concentrated to where they're less concentrated. But in this particular case, we are talking about only one molecule, the water molecule. And in this particular case, osmosis always means through membranes. Osmosis is not a term you would use unless you are dealing specifically with water and water movement, and you also have some kind of membrane involved. And so in this case, it's mostly cell membranes. So, for example, here's just a kind of graphical image of this. Take a look. Here's kind of a container that has water plus dissolved stuff in it. Here's a membrane that's dividing these two compartments. And notice on this side of the compartment, there's lots of solute. And on this side, there's not much solute. These little red dots represent the dissolved stuff, okay? Now, really, there's two conditions going on here. In this side, you have lots of solute molecules and less water. On this side, you have less solute molecules and more water. Now, if the solute molecules could move through this membrane, then they would certainly try to move back through this membrane and obey the law of diffusion. But most solutes can't move through membranes. So what can move? The water. Water can move through membranes. And so there's lots more water on the right than there is on the left. And there's lots more molecules of water on the right than the left. So those water molecules are definitely going to move through that membrane, and they're going to move from the right to the left, as it says. Okay? But you know what's kind of amazing about this? If you really did set this up this way, as the water moved from here to here, this water level would rise, because water is going to move, a lot of water is going to move from the right side to the left side, and it's going to make this water level go up and this water level go down. That's why you can actually create pressure. Here's the original setup, in which you've got lots of solute, less water, lots of water, less solute. The water starts moving this way, and take a look what happens. It creates an unevenness there. As the water moved from here to here, it caused the water level to rise. Let me show you real quickly. Ooh, where am I? Gotta find my documents here. Osmosis, a physical process in which water molecules move from where they're more concentrated to where they're less concentrated through a semi-permeable membrane. So remember, the word water and the word membrane are always going to be part of the definition of osmosis. And most membranes allow water to move through without any ability to control it. Water will move through depending on where it's more concentrated and where it's less concentrated. In fact, I created a rule called Mackey's Law of Osmosis. And this law says this: water will move through a cell membrane from where it's more concentrated to where it's less concentrated. It will move through a cell membrane from where it's more concentrated to where it's less concentrated. You see up here where I said the law of diffusion says if they can, they'll move if they can. Well, why didn't I put if they can down here? And the answer is because water can move through membranes to obey the law of osmosis. In living systems, water will move it will move through the membrane unimpeded because there are those aquaporins. Now, here's carrier-facilitated diffusion, a passive process where a special membrane protein helps a relatively large molecule that's impermeable to obey the law of diffusion and pass through the cell membrane. My favorite example of carrier-facilitated diffusion has to do with glucose, because glucose is much more common outside of cells than in. It would love to diffuse from where outside the cell to inside the cell, but it can't because it's too darn big. So the cell needs glucose, so it builds a special carrier protein exclusively for glucose to help glucose move from outside the cell to inside the cell. All right, so there's the law of osmosis that is mentioned elsewhere. Okay, reduce this. All right, so now let's talk about some very basic vocabulary that we need to talk about a little bit over here. Let me shrink this, because if you're really going to understand osmosis, you need to understand, have a clear picture of the difference between a solution, a solute, and a solvent. These are critical pieces of vocabulary. A solution equals the solvent plus solute. Right? So when you make a solution, it has a solvent plus solute. Now, in living systems, let me back it up and just say, in cells, solvent is always water, and the solutes are gases, ions, Klippin molecules, etc. So in cells, the solvent is always water, and the solutes are gases, ions, Klippins, etc. Now, here's what's kind of interesting to think about. Distilled water is 100% water plus 0% solute. Distilled water, the purest form of water, 100% water and 0% solvent, but solute, excuse me. But if, let's just say you have a 10%, 10% sugar solution. Remember, we did this when we played with eggs. 10% sugar solution equals 10% sugar plus 90% water. A 40% sugar equals 40% sugar plus 60% water. I mean, they always have to add up to 100%. Now, maybe you remember, we had eggs, and we put these eggs in 10%. We put them in a 0%, which was distilled water. We put them in a 10% solution, which was 10% sugar and 90% water. We put them in a 20% sugar solution, that was 20% sugar and 80% water. We put them in a 30% sugar solution, which was 30% sugar and 70% water. So notice that as the solute concentration goes up, as the solute concentration increases, misspelled. This is the solvent concentration decreases. So as the solute, remember these hard brackets here mean concentration. As the solute concentration increases, the solvent, which really means water concentration, decreases. So this is an important concept to think about. I don't know how many lectures I personally heard about osmosis before it finally sunk in what it actually was. I really felt like if you had asked me during, say, the first lecture I had, Steve, do you understand osmosis? I would have gone, yeah, I pretty much understand it. But if you asked me any detailed questions about it, you'd realize I didn't. So I don't know how many lectures, 2, 3, 4, 5, 11, whatever. It took me a while for it to sink in. And I can't give 11 lectures on it. So you might need to find another lecture on osmosis, which I would do by going to YouTube or to Wikipedia or to Google. And if you find that you just find this osmosis stuff too confusing, it might be that you need another lecture on it. But one of the most important things that some of these early lecturers did was they did not make sure I understood what it meant to be a solution, what it meant to be a solvent. Oh, good, thank you. So Tyler is mentioning that Khan Academy has great biology videos, no doubt about it. I mean, I watch them sometimes myself just to help me understand things better. So, but I think some of those earlier instructors who tried to teach me about osmosis did not make it clear that the intracellular fluid and the extracellular fluid are solutions. And that means they're made up of a solute and a solvent. The solute probably can't go through the membrane, but the solvent, that means water, absolutely can go through the membrane very easily. And so you have to think about the solute concentration and the solvent concentration in order to make good predictions about what's going to happen. And when they talk about solutions like this, they talk about the solute, that's what is dissolved, the solvent, what the solute is dissolved in, mostly water. And then they talk about tonicity, which is the strength of the solution, the concentration of the solute. But I'm inclined to define these terms like isotonic, hypertonic, hypotonic. I'm inclined to describe these terms based on the water concentration. So isotonic means that the concentration of the intracellular water is the same as the concentration as the extracellular water. Now, what does that mean about the solute? It means the solute is the same on both sides of the membrane. If the solute concentration is equal, then the solvent concentration is equal, right? A 50% sugar solution is 50% sugar and 50% water. Okay? Hypertonic means that the concentration of the intracellular water is higher than the extracellular water. So if the water concentration is higher inside the cell than outside, guess what's going to happen? Water is going to obey the law of osmosis, and it is going to leave that cell. And that cell is going to shrink. Now, if you put a cell in a hypotonic solution, well, now the concentration of the intracellular water is lower than the extracellular water. And that means that the water concentration outside is greater than inside. Water is going to obey the law of osmosis and move from outside to inside, and this cell is going to swell up. And if it is a ciliate, like the ones we saw earlier, if it's exposed to a hypotonic solution, it is going to swell up and burst. So we mean being aware of these different, of these sort of different scenarios is great. You know, I really, whenever I think about these kind of scenarios, sorry, I got to try something and just see if I can make this work. I need a Sharpie over here. And I don't know. We'll have to see if this will make it work. Somebody may tell me, oh, Steve, it's ridiculous. But I'll tell you what I'm doing. I'm drawing a beaker. And in that beaker, there's going to be a solution, of course. And then what I have just done is I have just plunked a cell into that beaker of water. All right, take a look. There's my beaker. Okay, here's the water. This is a solution. Technically, I guess we would call this the extracellular fluid since it's around the outside of the cell. That line right there is the cell membrane. This is the cell, and there's its nucleus. Okay. And then I'm hoping you can see two big question marks. Right? You can see two big question marks there. So I don't know. From what I can see, this must be pretty visible. So the question really is this: what do the question marks represent? What do the question marks represent here? Here's a poor cell. I just dropped it into a beaker. Question mark, question mark. Well, I'll tell you, these question marks have to do with osmosis. These question marks have to do with words like hypertonic, hypotonic, isotonic. And don't strain your brain too much about it, but because the answer to what these question marks represent is right here. Water concentration. The water concentration. If the water concentration on the outside and the inside are the same, Well, then the cell has been dropped into an isotonic solution. And equal concentration of water on both sides of the membrane basically means no effect. Water will not really be moving in or out of the cell in any concentrated way. Now, what if the water concentration outside is greater than the water concentration inside? Higher water outside than inside? Well, guess what? It's going to obey the law of osmosis and go this way. This cell is going to swell up, and if it's severe enough, and especially if this is like a red blood cell, it could burst open. Now, what about the opposite possibility? What if the water concentration here is higher than here? Higher, lower, the water's going to move from inside the cell to outside the cell. And as this cell loses water, it will lose weight and it will shrink. So we have terms for this. If anybody has any questions about that particular crazy document that I created right there, you could let me know. But we have terms for this. Prenation means cell shrinkage. The cell loses water loses weight. Why? Well, because water weighs 1 gram per mil. That loses water, loses weight. And gets smaller. Okay. Another term that we have is, well, the general term that we would use in this case would be, sorry, I got it wrong, hemolysis / cytolysis. You should be able to figure out what this actually means. Just look at the words. Hemolysis, that's the splitting apart of blood. Cytolysis, that's the splitting apart of a cell. Like when we saw those poor paramecium earlier and they were breaking open and stuff was spilling out, we were seeing cytolysis, the breakdown of a cell. If it was blood, then we would be seeing hemolysis. It means cell swelling, maybe even bursting. Oh, sorry, I wasn't showing you the word. I apologize. Hemolysis. Lysis means to split or cut. Hemo means blood. Cytolysis. Lysis means to split or cut. Cyto means cell. So if this was a blood thing, which could be very important, then these blood cells float freely in a solution. They have no real external support. If they start swelling up because water is rushing inside of them, they will swell up and burst. Now, cytolysis can also happen. And again, the best example of it is something we saw a little while ago when we saw the ciliated cell bursting. Let's look at that again, because what we're seeing there, it would be called cytolysis. Now, you know, of course, they're just sort of, all right, take a look. Water is flowing into the cell. It's causing the cell to rupture and all the cell contents. This one's going to happen too. Water is flowing into the cell. It's causing the cell to rupture and the contents are spilling out. This will certainly kill these protozoans for sure. Sorry, I started looking at that. Started looking too much at that video, trying to understand exactly what was happening there. All right, so again, that was what we just saw in those ciliates, was them swelling up because water was moving through the membrane inside of them. Why? It was obeying the law of osmosis. And then if the cell swells up enough and the membrane can't enclose it anymore, it's like a balloon that you've blown too much air in, and it just explodes, and that would be called cytolysis. So I'm just going to jump past this one. This is sort of what we were just talking about a minute ago. Take a look at this one. Take a look at this cell. Okay. It has a high solute concentration outside and a low solute concentration inside. But remember, the solute's not going anywhere. High solute concentration outside means low water concentration. Remember, the solute and the solvent are always inversely related. So what's going on here is this, the highest water concentration is here. A lower water concentration is here. So guess what? Water is leaving. It's obeying the law of osmosis. It's going right through the membrane. And what's happening to the cell? Crenation. Now take a look at this condition. We've got low solute concentration outside. So low solute concentration, where are you, cursor? Low solute concentration means high water concentration. High solute concentration means low water concentration. Remember, these are opposite. So bottom line is that on the outside of, this cell here, water is going to, it's high concentration compared to here. Water is going to flow through the membrane, and it's going to cause this cell to swell up until, again, it's possible that this cell could actually burst. We would call that hemolysis if this was a blood cell. Again, if a cell is attached in place, like the cells in our body, they are not going to swell up and explode because they are hooked together to each other by connective tissue, etc. And so they're not going to explode. If a cell is free swimming, like a paramecium, doesn't have any external support, and you put it in highly concentrated water, the water is going to move in the cell, and it's going to cause that cell to swell up and explode. And the same exact story is true for blood, is that blood cells are not supported. In fact, red blood cells, white blood cells, platelets, all of what they call the formed elements of the blood, meaning the kind of cellular stuff in blood, which would be erythrocytes or red blood cells, leukocytes or white blood cells, and thrombocytes or platelets. All of these are membrane bags. They are not attached to each other, and they are not able to give each other any support. So if you were to expose blood to a hypertonic or hypotonic solution, it would definitely affect the shape of that cell, right? It would definitely affect the shape of that cell. I mean, almost imagine that you're in this scenario again, where you're in this scenario again, and now you're asking, okay, this is a red blood cell. We just dropped it into a solution. What's going to happen to it? Well, it depends on the water concentration, right? The water concentration outside the cell is the same as the water concentration inside the cell. Then nothing's really going to happen. This is isotonic scenario, sometimes called a normal solution. If the water concentration is higher outside than inside, then the water is going to move inside the cell, and the cell is going to swell up and possibly burst. If the water concentration inside the cell is higher than outside, then water is going to move from inside the blood cell to outside. And as water leaves it, this cell is going to shrink and it's going to lose weight. Again, you know what? I wish right now that I had that egg data in front of me, because, and I think I can get it. but I'd like to look at our actual egg data and think about it in this context. Okay? I'm going to think about it in this context. Right. So take a look at this graphic right here, slide 25. Here is a normal red blood cell, and it is this normal red blood cell is in an isotonic solution. The amount of water that leaves is exactly equal to the amount of water that goes in. This solution is a normal solution, is what they actually call it. When they give an IV, they generally give an ID that they say the IV is a normal solution, which means it is the exact same concentration as the concentration inside of blood cells. So it doesn't damage them. They stay normal. We don't want to mess with our blood. Now, you would never, under any circumstances, expose blood cells to a hypotonic solution, because they would not only swell up, they would probably burst, and you would lose those blood cells, and that could be life-threatening. Same time, you wouldn't want to ever expose blood cells to a hypertonic solution, because hypertonic is going to make them shrivel up. The word I used earlier was crenation. And again, that's going to affect their shape, and their shape is super important for the job that they do. So the thing is, once a cell has ripped apart and burst open, there's not much you can do about it except make more red blood cells or give a blood transfusion. If they've shriveled up and they're crenated, then you could possibly put them in a normal solution and allow them to recover, and they might be fully functional after that. In a plant cell, the same kind of pattern is going to occur. If it's in an isotonic or normal solution, it's going to look normal, equal amounts of water in and out. If you put it in a hypotonic solution, water is going to flow in, but this cell wall that's always around a plant cell is probably going to prevent it from exploding. So it's just going to get really full of water and really tight and rigid. Now, if you were to put a plant in a hypertonic solution, that means water is going to leave the cell, and actually the cell itself will shrink. And sometimes when it shrinks, the cell membrane, which is right here, will actually shrink away from the it'll actually shrink away from the cell wall, and you'll be able to observe this. You can certainly see this if we wanted to look at a video of this. Okay. So Tyler just mentioned something about dialysis, and that sounded very interesting. Let me take a look. She wrote this. Well, you could probably read it. There are a lot of interesting examples about this within dialysis, where you have to make the right solution for each patient so you don't cause hemolysis or crenation. So basically, when you expose the red blood cells to, when you expose during dialysis, you're going to really expose the red blood cells to a solution that's designed to extract waste from the blood. And you really want to be really sure that it's not hypotonic or hypertonic. So you want to make sure that you don't cause either of those to happen. So thanks for mentioning that. That's a very interesting immediate connection. Okay, I gotta remember, I want to go to another document, but okay, so good. I'm not gonna go to that next document today. I'm gonna go to that next document next time, because that's when we're going to be starting to talk about active cell membrane transport processes. But what I'd like to show you here is, I'm just going to shrink this PowerPoint, and I'm going to go to a document that I've got over here somewhere. No. Oh, yeah. Wow. Boy, I apologize. I just realized I didn't look at this document, and this is a super important document. So I apologize. I have to back up, and I'll tell you why. We were talking about laws of diffusion, great, and we talked about cell membrane, and I even gave you some examples of diffusion in your home, right? I mean, I mentioned Oh, I mentioned in my particular case, I mentioned that I can smell litter boxes when I walk in the door thanks to the diffusion of odors from the litter box. I mentioned bacon because my mother's cooking that bacon in the kitchen diffuses all the way, way a long distance at the other end of the house, so I could smell it under the covers even. Honestly, I remember smelling perfume that I know is being sprayed at the other end of the house, but I smell it a long distance away. So these are good examples of diffusion in your home, but I want to give you an example of diffusion in your cells and a cell physiology example. And again, I'm going to apologize. I should have done this before I talked about osmosis. And, you know, I was actually kind of looking at the time and going, wow, I must be speaking a lot faster this time than I did the other day because I've got more covered in a shorter amount of time. And I don't know why. Well, now I realize why. And again, I apologize to sort of shift gears here, but that's okay. This document is posted on my PIMA, document 24, and it is called Gas Diffusion or Gas Exchange in the Body. And I really think this is an important example that I'd like to share with you of an important physiological event that's totally related to diffusion. All right, so this isn't bacon or perfume or litter box. This is diffusion in the body, and a super important example of diffusion in the body that you probably already know some things about. So let me show you what I've drawn here. And this document, again, is a document you have access to. It's document number 24, not in the Goldenrod packet, but on my PIMA. Okay, it's document number 24 on my PIMA. All right, so this is a story about the lungs and the bloodstream and the internal cells of the body and diffusion. First thing is, you see this kind of U-shaped thing that I've got here? This U-shaped thing is an air sac of the lung. These air sacs of the lung, the more technical term for them is they are called alveoli, and that equals the microscopic air sacs of the lungs. Right, so I'm just typing this in. These are called alveoli, but they're really the microscopic air sacs of the lungs. There are millions of them in each of your lungs. Okay? Now, I have deliberately drawn it this way. Do you see these cells right here? These cells are cells that are called simple squamous epithelial cells. Epithelium cells. And these are cells that are deliberately very thin and flat to promote diffusion. Oh, I know that sounds like a mouthful of letters. Simple squamous epithelial cells. These are thin and flat cells that are designed to promote diffusion. So it doesn't surprise me that the air sac of the lung is built of these cells. I mean, remember, structures in the body are built of cells. So here's one air sac of the lung. Now, right next to it here is the smallest microscopic blood vessels of the body, okay? The smallest microscopic blood vessels of the body are called capillaries. Okay, and these are the capillaries of the lungs. They're attached right to the alveoli. And it is not a coincidence that they are also built of thin and flat cells. Why? Because capillaries, these are the smallest blood vessels of the body. They come to within a few micrometers of every cell in the body, and one of their big functions is to promote diffusion, okay? The diffusion of gases, and sometimes some other molecules too. All right, so air sac of the lung, thin and flat cells, capillary, thin and flat cells. Now, these things inside that look like copyright symbols, those are supposed to be red blood cells. And then the stuff that's around them, the liquid part of blood, is called the plasma. Okay. So here's an interesting thing about air. Okay. The air that we breathe, what we call air, it is made of 78% nitrogen gas. Oops, misspelled it. Nitrogen gas, and that's N2. Okay, you can see it up here, N2, 78%. And I misspelled nitrogen, sorry. Okay. Plus 21% oxygen gas. Right? Plus, of course, if you take 78 and 21, you add 78 and 21 together, that's 99. And so the remaining other gases plus other gases, one of those is CO2. Pretty important gases make up the remaining 1%. Right, sorry, there's that data. Air is 78% nitrogen gas plus 21% oxygen gas plus other gases, including carbon dioxide, make up 1%. So there we've got 78, 99, and then some carbon dioxide, sulfur oxides, phosphorus oxides, nitrogen, oh no, not phosphorus, nitrogen oxides, radon, ozone. I mean, there's a whole long list of gases that make up that 1%. Okay, but when it's worth knowing that inside of our lungs, we have the ability to inhale about 5 liters of air, 5 liters. But most of the time when we breathe, we are breathing in what they call a tidal breathe. And that tidal breathe is just a little bit of air that goes in and out of our lungs. Like right now, when I'm breathing, I'm basically breathing like this. I'm just inhaling a little, exhaling, inhaling a little, exhaling. It's enough for me not to die and to continue talking and doing all that kind of stuff. So actually, I'm probably just normally inhaling about 500 milliliters. So 90% of 5 liters is, still in my lungs. Even when you're a cadaver, you're dead, you still have some air in your lungs. But when under normal conditions, when we do tidal breathing like that, we bring brand new air from the atmosphere deep inside the air sacs of our lungs. But the concentration of gases there is not the same as outside because there's a lot of stagnant gas down in here. There's gas that we never exhale. I mean, even the most highly trained, runner who can really maximize the amount of air they exchange in their lungs is not going to exchange more than a couple liters of air. The rest of it's just going to sit in there. So what that means is we're taking this mixture of air and we're mixing it with stagnant air that's in there, and we end up with numbers like this: 13% oxygen, 5% CO2. Right? These are the 2 real important respiratory gases we want to consider. Okay. Now, 13% oxygen, 5% CO2. Now, take a look at this vessel here. Remember, red blood cells, platelets, plasma, around it. Notice that the numbers I have for inside the bloodstream are numbers like this: 5% oxygen and 6% CO2. Now, I have to admit something to you. These numbers are averages. I had to look at all over the body and calculate an average, because the truth is that depending on exactly where you are in the body, you may have lower or higher concentration of these gases. Okay, but I took an average, and these are the average numbers. Now take a look at these numbers. Here's 13 and 5. Here's 5 and 6. And ask yourself this question: can I predict what's going to happen here? I mean, where will oxygen move and where will carbon dioxide move? Well, look, 13% oxygen, 5% oxygen, higher concentration, lower concentration. This oxygen is going to move from where it's highly concentrated to where it's less concentrated, 13 to 5. That's what this big blue arrow means. The oxygen is moving out of the air sac, the lung, and into the bloodstream. Now, at the same time, notice 6% CO2, 5% CO2. Now, this is nowhere near as big a concentration gradient, but it is a concentration gradient, so that overall carbon dioxide is going to move from the blood into the air sac. Super important process. We need to get rid of and ventilate CO2 all the time, otherwise it would kill us. So we ventilate it this way. It moves by diffusion. It moves by diffusion. Now, when oxygen leaves the air sac, the lung, and enters the bloodstream, when carbon dioxide leaves the bloodstream and enters the air sac, the lungs, there's a specific name for this. It's called external respiration. External respiration, I'm writing this down, is the exchange of gases between the air sacs of the lungs and the blood vessels and the blood vessels of the lungs. And what does that mean? Oxygen moves from air sac to blood. Carbon dioxide moves from blood to air sac. I hope I got this right. The definition: this is called external respiration, is the exchange of gases between the air sacs of the lungs and the blood vessels of the lungs. O2 moves from the air sac to the blood, see it, and CO2 moves from the blood to the air sac, you can see it. So it's an exchange of gases that happens as the blood passes the air sac. Okay? And you might think, well, wait a minute, Steve, why would you call this external respiration? Well, it's because, to be honest with you, this is about as close as the blood's ever going to get to the outside world. I mean, this distance right here, one layer of thin and flat cells, another layer of thin and flat cells, this could be like 50 micrometers. Here's the air you just breathed in, here's your blood, right next to each other. This is as close to outside of the body as blood is normally going to get. That's why we call it external, because it happened externally in the lungs. I mean, if you inhale something, it goes down in the air sac of the lung, and if it can, it will diffuse into the bloodstream, and once it goes in the bloodstream, it's going to go straight to the heart, and it's going to go up into your brain, and it's going to go to other organs within seconds, because that substance you inhaled is really close to blood vessels in the air sac of the lung. So that's external respiration. Now, it's worth asking a question. Look, you notice that this number here, 13%, 5%. So it sort of does enter my mind to say, okay, 13, 5, 12, 6, 11, 7, 10, 8, 9, 9, 9, 9, 9, 9. If it was 9 here and 9 here, it would be in equilibrium. but it never gets in equilibrium. We would die if it got in equilibrium. Why does this not just eventually even out? I mean, it's 13 and 5, and we know diffusion is going to happen. So 12 and 6, 11 and 7, 10 and 8, 9 and 9, 9 and 9, no more. It's in equilibrium? No, never happens. And you probably already guessed why. Okay? Look, is this a static condition? No. We breathe 14 times a minute. And every time we breathe, we refresh this. So it never gets, the oxygen concentration doesn't really get lower than this. It's constantly refreshed because we are inhaling brand new air into our lungs we inhale it 14 times a minute. So I was going to say every 5 seconds or so, right? Something like that. 4 and some odd seconds. So we're constantly inhaling. The other thing, of course, is the heart's beating and it's pushing this blood, right? Pushing this blood. And as it pushes the blood, it means that the blood is constantly being renewed and refreshed here. Okay. Thought it was a potentially interesting situation. Now, take a look. This capillary is going to ultimately lead back to the heart. And when the heart pumps, it's going to pump that blood into an artery, like the aorta is the biggest artery of the body. And then those arterial arteries are going to divide to form arterioles. And then those arterioles are going to divide to form capillaries. And now we are deep down in the big toe. This is a big toe cell. And we're looking at these big toe cells, or liver cells, or brain cells, or fingertip cells, whatever. I've always thought of the big toe cell as a cell that was just way out in the boondocks of the body, and it was completely dependent on the body to fully function, to provide it and meet its needs. So big toe cell is just my example of a cell that's out there in the boondocks of the body. Now, of course, there are capillaries out there in the boondocks of the body, and they bring blood down to these capillaries. These capillaries have thin and flat cells. Why? To promote diffusion. Now, down here, take a look. The blood concentration of oxygen and carbon dioxide is exactly the same as it is up here. Why? I told you, because these are average values. Okay. But then take a look in the big toe cells, and here's what it is saying, and I apologize that my writing isn't better. But what this is saying is that in the red blood cell, the oxygen concentration is less than 1%. It's very low. Might be close to 0. But notice the carbon dioxide concentration is dangerously high. It's greater than 8%. This is dangerously high level of carbon dioxide. It's tolerable. Cells will die if you don't ventilate this carbon dioxide. So take a look, because we're looking at the concentration gradient. 6%, 8%. So we know what's going to happen. Carbon dioxide is going to move from where it's 8% to where it's 6%. That arrow describes the movement of carbon dioxide out of the big toe cell and into the blood vessel. Now, at the same time, the oxygen that's 5%, it is absolutely going to follow this arrow so that it goes into a cell that has less than 1%, 5%, 0.5%. Of course, that oxygen is going to move from in the blood vessel into the big toe cell. Okay. This exchange of gases, where oxygen moves out of the blood and into the cell, carbon dioxide moves out of the cell and into the blood, this is called internal respiration, because this is going to happen deep inside the body. Internal, I'm going to give the same kind of description. Internal respiration is the exchange of gases between the deep internal cells of the body and their capillaries. They're very tiny microscopic blood vessels. Deep internal cells of the body and their capillaries. What does it look like? Oxygen moves out of blood into the deep internal cells, and CO2 moves out of deep internal cells into the capillaries. I'm going to double check this to make sure I didn't misspell any things, which I did. The capillaries, O2 moves out of the blood into deep internal cells. CO2 moves out of the deep internal cells into the capillaries. It looks fine. Here I am going to hit enter. External respiration is the exchange of gases. Whoops, I'm already down here. Internal respiration is the exchange of gases between the deep internal cells of the body and their capillaries. That's what we're looking at right here. We are looking at that right here, internal respiration. Okay. Gases between the deep internal cells of the body and their capillaries. Oxygen moves out of the blood into deep internal cells. You see it? Out of the blood. Carbon dioxide moves out of the cell. Now, you kind of know this story, because what's going to happen next, of course, is this blood is going to flow past these cells. It's going to lose its oxygen. It's going to pick up CO2. It's going to collect in venules and veins and go back to the heart, and then it's going to be pumped back to the lungs again. That's where it gets more oxygen, and it gets it manages to get rid of the carbon dioxide by ventilating it into the air sac of the lung. So one question that jumps into my mind here is, why is the concentration of oxygen in these deep internal cells so low? And why is the concentration of carbon dioxide in these deep internal cells so high? And the answer has to do with a third kind of respiration. It's this respiration down here that's called cellular respiration. Okay, it's right down here at the bottom. Sorry, can't make it stay up any higher. Oh, well, can I do this? Can I lift it up? No, I knew this. Should have known that wouldn't work. Okay, go back here. Now I'm talking about the third kind of respiration here that's called cellular respiration. Okay, cellular respiration down here at the bottom. I'm going to define cellular respiration on the chat line, okay? Cellular respiration equals the super important biochemical pathway. Maybe you remember a biochemical pathway is a series of reactions all strung together. Biochemical pathway that describes how energy is taken out of a glucose molecule can't even spell. Glucose molecule and transferred to ATP. Hopefully I didn't make any mistakes. Down here again to the very bottom, cellular respiration is the super important biochemical pathway that describes how energy is taken out of a glucose molecule and transferred to ATP. So take a look at the little equation here. Come on. Sorry, I wanted to copy this entire chat conversation. It sends me the chat conversation for what it's worth, but it takes a while, and it's not necessarily in a format that's super useful to me. But I apologize. Just give me a second here, because some of this stuff I want to save. I don't want to accidentally lose it like I usually do. Okay, good. Sorry. Okay, so I am here somewhere, aren't I? There I am. Okay. And we're way down here, though I may not be putting anything else up here. Okay. Right. So remember, the question was, why is the oxygen concentration so low and the CO2 concentration so high? We'll take a look at this very quick summary of cellular respiration, because here's what it says. In cellular respiration, we take a sugar like glucose plus oxygen, and they engage in a big, complicated biochemical pathway that produces carbon dioxide gas, water, and energy that goes into ATP. Right? I don't know why I can't, maybe it got cut off, but when I say energy here, I mean ATP. Now, what's the actual story? There's lots of energy stored in this sugar, like glucose. We need to take that energy out, and we need to transfer it over here to ATP, because most machines of the body run on ATP. Okay? So energy that's stored in this sugar, it was solar energy put there by photosynthesis, has to be transferred over to ATP energy, because ATP is what cells recognize. Okay? And that's the most common way they acquire energy. Now, that sugar is made of carbon, hydrogen, and oxygen, and the oxygen is made of oxygen. So notice over here we have carbon, hydrogen, oxygen, everything's accounted for. But here's the major thing. Oxygen is a reactant, and that means it gets used up. The minute that oxygen gets into the cell, it goes straight into cellular respiration and it gets used up. And that's why the concentration of oxygen is so low here. At the same time that you're using up the oxygen, guess what you are making? Well, you are making water. You are storing ATP. But you are also making carbon dioxide, a respiratory gas, a toxic respiratory gas, and you're making it. It's a product. So inside the cell, it's actually manufacturing CO2, and that's why the concentration is so high, and that's why it is higher in the big toe cell than it is in the nearby bloodstream, and it flows out of the big toe cell and into the nearby bloodstream. So these things are all pretty tied together, right? The external respiration, internal respiration, and cellular respiration. And in fact, many, many years ago, I was actually, probably the first semester I was ever in Tucson, I got really sick and I ended up in the respiratory intensive care, a place I hope to never see again. And I borrowed a respiratory therapy book from a respiratory therapist that came when I went into ICU, had nothing with me, and I was just bored, crazy bored. And I saw a respiratory therapy book and I thought, I'm going to read that book. But one thing that was in it that I was interested in was a detailed story of this, external, internal, cellular, which they referred to in this textbook as the respiration triad. Now, a triad is something that has three parts. So it has three parts. And they said, you know how to remember it? Remember this acronym, ICE. And just think for a second, what do you think that ICE stands for? All the words are right there in front of you. The I stands for internal respiration. The C stands for cellular respiration. And the E stands for external respiration. Now, for what it's worth, can't imagine that there's any other word you could make with I, E, and C, or any kind of acronym that would be helpful. There isn't any. And the reality is that does one of these come before the other? No. I talked about it external, internal, and cellular. But the truth of the matter is that this respiratory triad, this respiration triad is happening constantly in your body all simultaneously. Right this second in my body, every cell's doing cellular respiration. Every cell's is engaged in internal respiration, and there are cells involved in external respiration. So external respiration is happening right now when I'm breathing. Internal respiration is happening at the other end of that blood vessel loop, and cellular respiration is happening in every cell of my body constantly. So it doesn't really make any difference how you order them, but the ICE stands for internal, cellular, and external respiration, the so-called respiration triad. Okay, well, I'm going to reduce this document, and I'm going to fill the screen with my aged face, and I'm going to say that I'm ready to answer any kind of questions that people have. Because we are about to run out of time. Got a lot covered today. I'm going to most likely choose this video and post it once they send it to me. And I will post it as lecture number 5, or today's date is lecture 5. 1, 2, 3, 4, 5. Yeah, okay. Now, as soon as I end the class in a minute, I'm waiting in case there's any questions. Then I'm going to post the quiz. All right, I'll go immediately and post the quiz. All right. Thank you, Tyler. Everybody I'll see you at 2:15 on Thursday. Okay. So stay healthy, isolate, wash your hands 100 times a day, etc., and just do your best to take care of yourself and your family. Okay. And like I said, I will get the quiz posted momentarily. All right. Hang in there, folks. We're going to survive. Okay. See you on Thursday.